Andrew is a research fellow at Imperial College London, and he's going to talk to you about a laboratory model for assessing impacts on transmission and how that model can be used when developing a TBV.
Good morning, and thanks for inviting me. So very briefly, I'm going to talk very briefly about some of the work we've been doing on the assessment of antimalarial transmission blockade within laboratory populations of both mosquitoes and vertebrates, and hopefully this talk will dovetail quite nicely with the work Tim was just talking about, assessment in the field. I'm going to talk a little bit about assessment in the lab, some of the advantages of this approach, and some of the areas where we've got to have caution when putting lab findings into the field. So very briefly at the moment, as Tim's mentioned, we're very lucky to have a wide range of lab-based assays to look at malarial and transmission blockade. So some of the assays are described on this slide, and some of the parasite stages they examine along the top of this slide. So very, very briefly, we have numerous early or late-stage gametocyte assays that look from stage 2 all the way through to stage 5 mature gametocytes. We have various exflagellation or macrogamete assays that look at the conversion or the activation of gametes into motile gametocytes into motile gametes. We have organic conversion assays. We have the gold standard assays traditionally that Tern was mentioning, which is the standard membrane feeding assay, direct membrane feeding assay, direct feeding assay, or skin feeding assays that all use oocyst intensity and prevalence as their output. And then we have various sporozoa assays available to us as well. So all of these assays are of course very good in their own way. They give us very, very valuable data, and they're very good for triage of new transmission blocking vaccine candidates. However, all these assays really have the same problem in that by using them, we're not actually measuring the desired endpoint of transmission blocking vaccine usage in the field, which is reduction in subsequent infection in a vertebrate population. You can express that in numerous ways in the field: impact on the basic reproductive number, R0, parasite prevalence, force of infection. Instead, all of these assays rather conveniently measure intermediates only, namely reduction in parasite burden in the mosquito. So that's not the only problem with the assays we've got at the moment. The other issues we've got with our assays is they don't really inform us what efficacy is required for a successful transmission blocking vaccine. To put it very bluntly, we still don't really know what a successful transmission blocking vaccine looks like, and our assays don't really provide us with any information regarding this. Secondly, and it's a point related to the first point, in that we still don't really know what variables impact upon this efficacy. As an example of this, transmission in the field is highly, highly variable. Therefore, the efficacy we'll need for a successful vaccine is going to be very, very variable. And our current assays don't take any of this into account. So therefore, we still don't really appropriately know how to use TBVs in the field. My third point is all of these assays only examine a single point within one cycle of transmission. That, of course, isn't how transmission works in the field at all. We've got concurrent rounds of transmission occurring one after the other. So how relevant is the data we're really generating in the lab? There's obviously a real disconnect between our lab and field assays, and it'd be very nice to try and reconcile that data. And fourth, and it's a purely practical point, if we're going to use a transmission blocking vaccine, we will need regulatory approval. In order to get this, it would be very useful to demonstrate an impact on a vertebrate population, and our current assays don't do this. So we've come up with a very brief model that helps towards solving some of these issues. It's our laboratory population transmission model, and it's a very, very simple mouse-to-mouse model using the rodent malaria parasite Plasmodium berghei to measure the efficacy of any transmission blocking agent on the ability of malaria-infected mice to transmit malaria to another population of naive mice by mosquito bite. So in this model, we're directly measuring the effect of a transmission blocking vaccine on transmission. Firstly, from vertebrate to vertebrate, we're not just looking for vertebrate or insects, we're actually measuring the desired endpoint of TBV usage. Secondly, we're looking at different transmission settings. So within the scope of our assay, these are called different mosquito biting rates, or MBRs, and it's simply the number of potentially infectious bites per individual mouse within the model, and it's a pretty crude attempt to simulate AIR in the lab. It's important to note that it is a crude attempt to simulate AIR. It's as good as we can do in the lab, so we've got to be quite honest about that shortcoming. We've got a very homogeneous mosquito population, homogeneous biting times. Thirdly, we're looking throughout the entire parasite life cycle over multiple cycles, so it's not just one pointer output, and as a result of that, of course, we've got very, very high biological content. So, of course, a caveat to the model, and it's blatantly obvious to everybody in the audience, probably, is that we're using a rodent malaria parasite for this. And we've got to be quite honest and open and say that this is a model that you can use to inform field studies, and that's as good as it gets. P. berghei is a fantastic model to look at transmission, and we should be very positive about using it. It really is a good model. It's very cost-effective, very robust, and of course, these studies would be completely technically and ethically impossible to do in any human parasites. So how do we perform our model? Well, we do 5 rounds of vertebrate to mosquito to vertebrate transmission. We start by taking 5 mice, which are infected with Plasmodium berghei mechanically, just by injection. We then leave those mice for 10 days, and after 10 days, gametocytes from the peripheral blood and are maximally infectious to mosquitoes. We then treat our mice with our test TBI, either a vaccine or drug, or negative control. And then we feed all 5 mice to 500 Anopheles stevensii mosquitoes. So we've got the parasite population out of the initial vertebrate population into a mosquito population. We then, 10 days later, take a 50 mosquito sample and look for oocyst intensity and oocyst prevalence. So it's exactly the same sort of data as we get from normal membrane feeding or direct feeding assays. The difference is we've got 450 mosquitoes remaining, so we leave those remaining mosquitoes 11 days. At that point, sporozoites are in the salivary glands and a maximally infectious new host. So then we plot a preset number, which is our transmission setting, our mosquito biting rate of randomly selected mosquitoes 5 times, expose these to 5 naive mice, and essentially let these mosquitoes feed on these mice at individual biting rates. So we've got sporozoite numbers in salivary glands after each bite. We can relate that back to oocyst numbers, we can relate that back to previous infection, but crucially, we can also relate that forward to subsequent infection. So from days 6 to 10 post-bite, we smear each mouse daily, and we look for parasitemia, community-cytemia, and then the really important one is their presence of infection. So this is measuring the actual number of malarial cases in vivo in real time in a laboratory model. And we can look at the effect of our transmission-blocking vaccine on that in comparison with a negative control. As I mentioned, we do successive rounds of transmission, so these 5 mice are then taken, and the whole cycle goes round again, and again, and again, and again, 5 times. So we get a huge amount of outputs over these 5 transmission cycles. We get parasitemia and community-cytemia in our initial mouse populations. We get oocyst and sporozoite intensity and density, and prevalence, We get, in the secondary mouse populations, we get parasitemia, and we can calculate pre-patency for that, because we're measuring data across time. We look for community-cytemia, and then, as I mentioned previously, the crucial output is the number of naive mice that become infected after mosquito bite. So that's actually a measurement of the number of secondary new malarial infections at individual transmission settings. So to get this model working in the first place, we've done quite a lot of preliminary experiments, as you'd imagine. And to get this assay model off the ground, we've initially mainly used a transmission-blocking drug. The drug we use is atovaquone. We've used it because it's ridiculously stable and very, very easy to use. You get very robust and reproducible results. And crucially, we can achieve any desired efficacy we want using atovaquone very quickly, very cheaply, and very easily. So as an example, with our initial experiments, we picked a dosage of 0.5 micrograms per kilogram, and we did a classical transmission blocking effect using direct feeds. You can see the results here. So in blue is our negative control with no drug, and then the red is through replicates with our drug. A number of oocysts per mg along the side, and infection prevalence is along the top. And in summary, we see a reduction in oocyst intensity of 57% and a reduction in prevalence of 32%. So this is a partial efficacy only. It's a TBI that we would practically consider as useless compared to others out there, and I'll come back to that later. So then, as I mentioned, we perform the assay and we get a huge amount of outputs. The 3 most important outputs are here. So there's a series of graphs. You can see on the left-hand side of the slide, there's a graph that's mainly blue, and that's prevalence of blood-stage infection in the vertebrate population. And then you see the other 2 oocyst prevalence and intensity in mosquito populations. So each graph has number 1 to 5 along the bottom. That's the observation. That's when the observation was made, the transmission cycle. And you can see as you go down the graph, the number of bites increases. So at the bottom of the graph, it's higher levels of transmission. At the top, it's lower levels of transmission. Each graph is a light and a dark bar. The light is in the absence of TBI, and the dark is in our presence of our TBI. So the main obvious point is that at low mosquito biting rates, that's 1 or 2, everywhere above this red line, we see progressive reduction and elimination of mosquitoes, of parasite from our mosquito and vertebrate populations by generation 2. Or generation 3. And that's with our low efficacy TBI. This is something that you previously considered to be absolutely useless, but at specific transmission settings, it may have an application. And then the second obvious point is that higher biting rates, we don't see any measurable impact at this transmission level. But as I mentioned previously, what we really want to do is attempt to give our data some kind of field relevance. And we can do this by expressing it as impact on the basic reproductive number, or R0. Do this by calculating something called effect size. So an effect size is a single number that's the magnitude and reduction in the basic reproductive number due to use of a TBI. It's very well described in Pete Gethin's paper in Nature in 2010, if anybody's interested. And by using it, we can measure the ability of an intervention to reduce the probability of transmission, firstly, from vertebrate to vector, secondly, from vector to vertebrate, and 3, across multiple transmission settings. So it's a real attempt, with the caveats of taking any lab-based model and putting it in the field, to give our data some kind of field relevance. It's much more translatable than looking at something like oocyst intensity or prevalence. So we calculated from our data by fitting a chain binomial model to it. That's at the MRC Centre of Outbreak Analysis and Modelling at Imperial. And the idea by using effect size is to inform the field requirements for TBV efficacy using a lab-based model. We can do this by overlaying effect size onto disease endemicity maps. So an example of that is here. You can see we've got a transmission partially efficacious transmission model intervention, gives an effect size of 20.4%. So what does this mean? Well, this means assuming 100% coverage and constant efficacy. If we were to use it globally, you would see a reduction in R0 of 20.4%. What this would mean is anywhere where RC is 1.255 or below, you'll see elimination. That's the yellow areas on this map. The blue area is the area where elimination wouldn't occur. And these yellow areas are actually 74.77% of malaria affected population. That's actually quite a high number, and we were pleasantly surprised by that. But it's a real indication that the efficacy you need in one area is not going to be the same as the efficacy you need in another area. So to take that slightly further, we've used our model for 21 different interventions to date, all with varying biological activities and efficacies. We've looked at multiple transmission blocking drugs and multiple concentrations, both oral and IV delivery. We've used transmission blocking monoclonal antibodies and pre-orthostatic monoclonal antibodies delivered IV to mice post-injection. In total, we've achieved reductions in oocyst prevalence ranging from 100% to minus 15.6%. So we see complete inhibition to no inhibition, and the same for reduction in oocyst intensity. But as I mentioned previously, what we really want to do is relate these traditional oocyst assay outputs to effect size to look at impact on R0. So these two graphs describe these are preliminary data, but it describes the relationship so far. So the graph on the left-hand side is a relationship between reduction in intensity and effect size on the y-axis. On the right-hand side, we've got the percentage reduction in oocyst prevalence compared to effect size. So you can see there's various points. We're trying to collect more data to fill these graphs out as we go along. But you can see the relationship between the two and along. Drawing a line of best fit through those. So the real idea is to link in some way lab and field relevant data with the usual caveats. And I'll come back to why measure effect size. The idea is to overlay onto current global malaria maps with the eventual idea of informing efficacy requirements for a successful, or what you count as a successful transmission blocking vaccine prior to any phase 3 trials. So as an example of that, we can look at this line and we can take a 25%, 50%, 80%, and 90% reduction in oocyst intensity. We can see the relative effect size we get from that, and then we can look at field impact. So as a brief example of that, with our current data, this is a 25%, which you can't see, but this is a 25% reduction in oocyst intensity. Gives an effect size of 44.54%, and the yellow areas are with 100% coverage, what you'd expect to see elimination at. If you up that to a 50% reduction in oocyst intensity, you'll see an effect size of 75.83%. And again, the yellow areas are the areas where you might see elimination. If you up that to 80%, you'll get an effect size of 95.89%. Again, the situation is clearer. And if you up that all the way to a 90% reduction in oocyst intensity, you'll see an effect size of 98.33%. Anywhere where RC is 60.024 or below, you may see elimination with 100% coverage. So the main two take-home points from that is that effect size can be a powerful tool to consider potential TBV efficacy requirements, and it's not one of the lab scientists were traditionally considering. Maybe we ought to start. And the second point is there is no single global efficacy target for a successful transmission blocking vaccine. The target efficacy you require is going to be completely dependent on local transmission levels or R0 levels in that area. So in summary, it's a text-heavy slide, so I'll condense it, but we've got a high biological content lab model that can address multiple questions on parameters defining TBV efficacies in different populations. And then the three main take-home points are in red here. We really need to start considering the action of TBVs over multiple transmission cycles. We're not doing that during our current lab-based assays at all, and we should start considering it at least. Secondly, we really need to consider transmission setting when setting TBV efficacy requirements. And there is no single target efficacy for a TBV that will achieve elimination. This model with caveats can allow extrapolation to the lab, but those caveats do have to be strongly considered. I want to emphasize that. And finally, effect size should be considered as a useful parameter when assessing TBV potency. So if you choose the model, we're particularly interested in looking at coverage. All of these outputs assume 100% coverage. That's how we've used the model so far. We can actually look at different levels of coverage and see what efficacies we need. We're also looking at humanized transgenic parasites, looking at combinations of TBVs with their interventions. We get a lot of data to give to modeling, and of course we can use drug screening as well. So all that's left is to thank people, particularly everyone at Imperial College, Liana Upton, Kasia Sala, Mark Tunnicliffe and Sarah Zakatansky have done a lot of the work, so if you've enjoyed it in any way, it's due to them. Thanks to everyone at the MRC Centre for Outbreak Analysis and Modelling, Pete Gethin at the University of Oxford, Didier Marybeth from MBI Path, and Didier Leroy, special mention from MMV. Thank you very much.